The objective of the presentation is about that how to understand the various systems and the block diagram reduction tool using the MATLAB. So any system can be represented in this form, that is in the ratio of output to the input. So where the system function is generally referred as the transfer function. So in this case, the transfer function is nothing but the ratio of output signal, Laplace of the output signal to the Laplace of the input signal taken with zero initial condition. So a system, it can be a combination of any n number of such transfer function, and it can be connected in any way. That is, a system can be two systems can be connected in series or parallel, or a system may have that feedback with the single loop system and other thing. So first, for an example, let us consider what is the net transfer function when two systems are connected in series or cascaded, and then how to find the transfer function of it. So here, when two systems are connected in series, means when the output of the first system is connected as the input for the second system, then it is referred that both the systems are connected in series. So if you see here, g of s is the transfer function of the first system and gcs is the transfer function of the second system. The external input is applied to the first system, and the output of the first system is going to act as the input for the second system, and the output of the second system is the global output y of s. Our ultimate objective is to find out what the transfer function of the resultant system, that is y of s divided by r of s. So now when both the systems are connected in series, so it's simply that when input, when passing through this g of s, it will be multiplied by the system function g of s, and the output of the first system will be r of s into g of s, and this r of s into g of s is the input for the second system gc of s. So while arriving at the output y of s, then y of s can be represented as g of s into gc of s into r of s. A very simple example what you can consider for this system is, you consider this is your mobile phone, and this is the transfer function of your audio output in a car, or you can use you can connect some external speaker. Okay, so the final sound output of the system and the primary input is going to be from the music file whatever stored in your mobile phone, and it has its own volume control. So the output volume of the mobile, or that is in the audio jack, is going to be the magnitude of the output is going to be based on the volume function, whatever volume level what we are sitting in the mobile. And when this is connected to the input of your speaker, what you connected externally, then the sound output of the speaker again is proportional to the gain adjustment which is provided in the volume adjustment which is provided in the speaker. So what will be the net output? Let us, for an example, if we consider, I am keeping volume 0 in the mobile. So here I won't get any sound output. So obviously here it is 0. Whatever the volume I keep here, then the output will be like, I won't get any sound output. Let us say I am keeping 50% volume in the mobile, and here I am keeping only 10% volume in the speaker. So what will be the net output? The net output will be lesser than the output from the mobile. Okay, and again in this case, just for an easy understanding, let us consider both the speakers are providing the same volume as the output, same sound level as the output. So if we are considering in this case. So now how to implement this, or how to find the transfer function of the system using MATLAB. So as we discussed earlier, so any system function can be represented in the form of transfer function as a by considering two variables, numerator and the denominator, in the matrix form. So here in the numerator of g of s, it is taken as 1, 1 because considering the coefficients, and the denominator it is denominator 500 s square, and there is no term associated with s and the constant coefficient, so it is represented as 500 0 0. And come to the second, when you come to the second system GC of h, in the numerator the coefficients are 1 and 1, and the denominator coefficients are 1 and 2. So we have this numerator of h is declared as 1 comma 1, and the denominator is defined as 1 and 2. Next is the net system will be then the series combination of these two systems. So I am creating one system variable, numerator comma denominator as matrix is equal to series of num g comma den g comma num h comma den h. So once you give this command, then automatically it will take the MATLAB will take this is the first system numerator, first system denominator, second system numerator, second system denominator. Both the systems are connected in series. So like this, if you have n number of systems, then you can provide n number of inputs here, and all the systems will be connected in series. And I want to get the output printed on the command window. So once you execute this yum file, actually all this thing you can either do in command window, or else you can directly do in the using a yum file also. So the output will be displayed on the screen as s plus 1 divided by 500 s cube plus 1000 s power 2 is the net transfer function. Here actually s plus 1 the whole square. And then you consider a simple feedback system. So in this case, RFS is the universal input and YFS is the output of the system. Here you see the signal, it has two transfer function, G of S and H of S. So G of S is the forward transfer function, means the signal flows from input to the output side. So this is a forward path from input to output. If you take the H of S, the second system, the input for the second system H of S is derived from the output, and the output of this H of S is given as given back to the input side. So this is called the feedback network. So in order to differentiate the forward gain and the feedback gain, the terms are represented with the letter script, that G of S for the forward path and H of S for the feedback path. And this is the summing point where the signals are combined, that is your two signals are combined. Here the RFS is one your input signal, and the another signal is nothing but the output of the feedback block. So here, according to the signal polarity, the signals will be combined. It is, or else it is called summing point or the error detector. So normally, whether the signal, both the signals are additive, or it is going to be the difference is going to available at the output, that is indicated here. So for an example, if you take RFS is given to the plus and this feedback input is negative to minus, so here I will get RFS minus the output of this feedback path. Suppose if both are connected to positive, then it is represented as a positive feedback system. So in the positive feedback system, I hit at this output of summing amplifier will be that RFS plus the output of the feedback network. If it is a negative feedback system where RFS is connected to positive and the feedback signal is connected to negative, then I will get RFS minus the feedback signal. Okay. And so in this case, how to represent the system? So similarly, as in the previous case, the system representation is going to be in the same way as how we did in the previous system. Like the numerator function, the polynomial, and the denominator polynomial will be defining for both G of S and H of S. So num G den G indicates to the parameters corresponding to G of S, and the num H den H represents the polynomial coefficients of the polynomial in the denominator and the numerator and denominator respectively. So again, I am going to create one system, the net resultant of the system. How to get this? It is using the feedback command. I am going to take it. So feedback of first system, comma second system, comma the type of feedback. This is the template. That is feedback of numerator polynomial of the first system of the forward path, comma denominator of the forward path, comma numerator polynomial of the feedback path, comma denominator polynomial of the feedback path, and then the type of feedback. It is the value is 1 for positive feedback and -1 for the negative feedback. So once you execute this, you will get the output of the system like this. Now this command of feedback and this feedback command can be used only for a simple feedback system like this. Now if you have multiple feedback systems, then in that case how it is been considered. In the case with your system with multiple feedback loop like this, we'll be going with a new command called block build. Okay, first let us have a look at the system. The system has the it has the feed forward path, or it is the one forward path. C of S is the output and R of S is the input, and this is a path traveled by the signal from input to output. So this is a forward path, and if you take here, it has one feedback path and again another feedback path and again another feedback path. So it has totally 3 feedback paths with the gains of H1, H2 and H3. And apart from this, if you see, there is one more path which is flowing from the which passes the signal from input side to the output side. So this is also another forward path available in the system. And so altogether, the system, this entire system has 7 systems distributed in the forward path and also in the feedback path. So let us assume the system functions given like this. G1 of S has the value of 1, G2 of S has the value of 1 by 1 S plus 1, G3 of S value is 1 by S plus 2, and G4 S value is 1 by S plus 3, H1 of S is 4, H2 of S is 8, and H3 of S is 12. And again in this case, either the gain functions G or H, either it can be a constant or it can be a polynomial of S. It may be of nth degree also. So again here, in order to transform or in order to find the transfer function of this network of this system using MATLAB, I am just going for numbering the blocks 1, 2, 3, 4, 5, 6 and 7. So totally I have 7 blocks in the system. Okay, so I need to give all the information. I need to see I totally have 7 transfer function corresponding to 7 blocks present in the system. So I need to provide all the information regarding the systems to the MATLAB, and then I have to transform how the systems are connected, how the blocks are connected. And you just observe here plus minus plus minus plus plus minus like that. So all these points we need to observe. So next we are going to see how it is transformed into code to deal with the MATLAB software. You can see here, for implementing this block build command, what are the necessary things we need to do is, we should first define the system numerator polynomial and the denominator polynomials with the template of ni di. Ni indicates the numerator of the ith block and di indicates the denominator polynomial of the ith block. So totally we have 7 blocks in our system, G1 to G4 and H1 to H3. Totally we have 7 blocks. So we have to represent in the first 7 lines. If you see that, we are defining the system transfer function. For the constant coefficients, let's see here for G1, H1, H2, H3, there is no denominator polynomial, which means that the denominator value is 1 and the numerator is a constant. So in that case, how we are defining for block 1, the gain value is 1, g1 of s value is 1. So the numerator value is 1, denominator value is also 1. For g2, 1 by s plus 1. So numerator polynomial is 1 and the denominator polynomial is 1 comma 1, means s plus 1. So in the similar way we are representing up to the 7 blocks. Then we are giving the input that how many blocks present in the system. So totally 7 blocks are present in the system. So we are defining n blocks equal to 7. Then I am calling the command block build, blk build, which means it is going to develop a block diagram for all the systems. And I need to from the first 7 lines I have given the inputs regarding the system. In the 8th line I have given totally how many blocks are available, and I called upon the block build function. Next I need to interpret the MATLAB that how the several blocks are connected and where it is receiving the inputs, each and every block from where it is going to receive the input. So in the first column, if you see, we have taken 1, 2, 3, 4, 5, 6, 7. So which means that I am defining a Q matrix in which first column has the block numbers 1, 2, 3, 4, 5, 6, 7 blocks, and in the subsequent columns I am going to give the information regarding where the particular block is going to take its input from. So if you take the first block, all the entries are 0, which means it is not receiving input from any other blocks. You can see here for the first system the input is from the external world, the global is the input, it is the input for the entire system, and it is not receiving signals from any other blocks. So that is why all the entries are 0. If we take for the second block, here the inputs are the output of the first block and the output of fifth block, and you see here both the signals are combined using a summing element. So where the first output is connected to positive and fifth output is connected to negative. So how I should represent is 1 and -5, and it is receiving only 2 inputs. Your block 2 is receiving only 2 inputs, one from block 1, the another from block 5. From block 1 it is connected to positive, from block 5 the output is connected to negative. So that's why the entries are 1 and -5. Similarly for block 3. So block 3, if you take here, it has one input signal which is combined using the summing block. So to the summing block I have 2 inputs, one is from block 2, the another one is from block 6. Block 2 output is connected to positive of the summing amplifier, and block 6 output is connected to minus of the summing amplifier. So the entries will be 2 and -6. Then we'll come to the fourth block. If you take the fourth block, it has one input coming from the summing amplifier, and to the summing amplifier I have 3 inputs. So if you take that, one input is from the feed forward path, that is before G3. So here what is the signal available? Here signal available is 2 and -6. 2 and -6 are available here, and from here +3 is available, and from here -7. So you have that 2 -6 +3 -7 are the 4 inputs for the block 4. And similarly 5, the element 5 is in the feedback path. The element 5 receives its input from output 3 of the output of the block 3. So that's why the representation is 3. Similarly for block 6, For block 6, the output is from 3. For block 7, the output is from 4. So wherever you receive the inputs, you make the corresponding entries with space. Okay, and wherever no inputs are there, no entries are there, you just mark it with 0. First block doesn't receive any input from any other block, so all the values corresponding in the corresponding row are made 0. And here block 2, it has only 2 inputs, so all others are 0. In a similar fashion it is performed. So how many rows that Q has and how many columns does Q has? The number of rows in Q matrix is equal to the number of blocks present in the system. The number of columns other than this block number is equal to the maximum number of the connections, maximum number of interconnections available in the given system. So here if you take in this system, only the block 4 receives the maximum number of input. That is here 2 input, 3 input, 4 input. So that's why we have totally 4 columns indicating the interconnection. We made it. And next we need to say to which block we are giving the input and to which block we are taking the global output of the entire system. If we take here, input is to the block 1 and we are taking the output from block 4. So I am declaring two variables, input and output. Input is block 1 and output is block 4. Okay. So I provided all the information regarding the connection. Then I need to interconnect all the systems. So for that I need to use the connect command. Okay. Once I use the connect command, the block build, what it does actually, it will consider all the systems in the state space form, ABCD format. So it will take, once you give connect, the ABCD values of whatever the number of blocks you provided, it will be absorbed, and all the ABCD of variables of the 7 blocks whatever we are given is combined using the possible interconnections provided in the Q matrix by considering the input node and output node what we specify, and it will calculate the ABCD variables, that is it will calculate the state space values of the system, or it will calculate the state space matrix of the resultant system. So the resultant system will be a state space matrix like this. Next, our ultimate objective is to compute the transfer function of the system. So what we used to do is we need a transfer function from the state space. So we use the command state space to transfer function ss to tf. If you use this command, within the parentheses you are going to feed the ABCD variables of the system. The output will be the numerator and the denominator, which is nothing but the transfer function of the system. So once the print syscom command is executed, so it will give the ratio of numerator by denominator is equal to the transfer function of the system. Thank you.